and thank you for being here at the conf. My name is Dotan. I'm the CTO of the Guild. Here with me today, Kamil, my friend and colleague. Today we're going to share and demonstrate a project that we worked on in the past year. But first, I'll start with a quick overview of who we are. So we are the Guild. I'm sure that you already heard of us today a lot. You've probably seen our logo everywhere. We're in the GraphQL business for over 10 years, and our work is mostly around open source tools, open source products, and they're all around APIs and GraphQL. The Guild is as old as GraphQL. We are doing this for 10 years, already said. So we are very proud of what we're doing. Our ecosystem is built, we started as a consultancy, and with time we learned from our customers what are the actual needs that they have. So from that, we did libraries, and the libraries helped them to solve ad hoc problems. And then when we realized that we can build bigger tools, more solutions around it, not just libraries, we built Hive, our first SaaS offering. It's a schema registry, and then we added a gateway to it. Last year, we acquired Stellate, an edge caching solution, so this is also part of our stack. And if you are in the GraphQL business, and I assume you are, you already know us from Mesh, Yoga, Cogen, and a lot of other tools. Today, I'm here to talk about a new library and a tool that we announced a few days ago, Hive Router. We are very proud to share this journey with you because it's not just a new product, it's also the most performant federation router in the ecosystem. You can see some numbers here. Kamil will explain how and why it's so fast. But yeah, I can only say that it's like very fast, and we'll dive into the details in a few minutes. It's not just fast, it's also very efficient in terms of CPU. It's very efficient in terms of memory management, and we beat all other gateways and routers in all metrics. So stay with us. But that's not all. In the past year, we also worked on a new query planner. A query planner that is 100% compatible with Apollo Federation. It's full open source. You can use it in any project. It doesn't have to be with a router. It's just a library, but it's baked into our new router, and you can use it to get full execution of Federation. As I said, it's all open source, but real open source. And that means it's MIT. You can use it, you can fork it, you can extend it, you can do whatever you want with it. We do not gate any features. This is a very important concept at the Guild. When we do open source, we do it the right way. You can use our product, our tools, just the way you want, and we give you access to all the features. So this is a very important thing for us. And one more thing, it's not just open source today, it's open source and it will always stay open source with the same license. We promise you. So I'll start with a quick overview of how it started. So I said before that we started as a consultancy for GraphQL, and this is where our first interaction with customers began. So we listened to our customers, and they wanted products, and then wanted tools, and they wanted managed tools, so we built it. But then with time, we realized that now we are building a product, and listening to our customers is even more important than when we did just consultancy. So this is how we started. We listened to our users, to our customers, and they told us what they need. And it was very important for us to get that feedback, because this is what helped us to shape the last year of work at the Guild. So our journey with Federation started around 2021. Apollo Federation V2 spec was just released. shortly after, it became the industry standard for building distributed GraphQL at scale. We loved the idea and adopted it. 1 year after, we introduced the full composition for federation in our schema registry, Hive console. 2 years ago at the GraphQL Conf, we released and shared with everyone our benchmark for GraphQL gateways for federation. It measures performance, it measures everything that you need to test in your GraphQL gateway. Last year, we did a similar benchmark, but this time for compatibility. We wanted to make sure that we're not just performant, we're not just running cool features, but correctness and accuracy of the gateway is also on the highest standard. So we released that and we made it public for everyone to use. Also last year, we released Hive Gateway v1. It's our JavaScript gateway. It's fully featured, and I'll talk about it in a minute. We have a few announcements in this conf. I'll dive into that in a second. But before that, I want to, did it work? Didn't work here, okay. But before that, I want to talk about compatibility and the federation audit. And Kamil, you take the stage.
Sure. There are no notes. So yeah, when we first started I think it was like 1 year ago, we first published the Apollo Federation Compatibility Audit. And at this point, when we released it, some people were questioning it. And they were saying that like the many of the spec details we tested weren't really like real-world production workloads that people experience. But the truth is that those weren't just hypothetical edge cases. There were like real production issues that our users encountered, and we turned them into tests in order to like fix the things we had and like turn it into like a to never get into those bugs again. And if you look at this chart, like in late 2024, like Cosmo and GraphBase were like quite far behind. The GraphBase was around like 50%, Cosmo around like 70, and after the audit went public, those scores steadily climbed, and today they both exceed 90% compatibility. Hive started at 100%. That's like obvious. That was our test cases for the Hive gateway, and we were like almost consistently at the 100%. There's just one dip in like, I don't know, 2024 at the end of the day. Apollo is constantly hitting the almost near perfect score. And what does it really mean is this, like the audit didn't just measure the compatibility, it showed like real gaps that users were hitting in their production environments with different gateways. And like the same cases happened to other gateways that, for us, it happened with the Hive gateway, we encountered them, so added this as a test for the audit. Other people discovered those issues also with other vendors, so they shipped the fixes. That's why the audit score grew over time. And so at the end of the day, all gateways improved, which is like, that was my goal with creating the audit. Yeah, that's my part. No, it's not the stuff.
You'll be back, don't worry.
Yeah, I'll be back.
So we'll go back to this slide. We talked about the compatibility that we did last year. And we had a release of Hive Gateway v1. I want to talk about Hive Gateway for a minute. So it's full open source. The only thing we ask from you is for your feedback. And if you have issues, please report them and don't ignore them. You can join our community. Many companies and many of our customers are migrating and moving to Hive Gateway. And I wanted to say that JavaScript is not going anywhere. It's a very important piece of tech that we have built in the past few years. It's using a lot of other tools that we built, like GraphQL Yoga, Envelope, the plugin system. It's using GraphQL JS itself, obviously. And it's full open source and it's fully featured. So if you are looking for a gateway that you can easily extend, control everything going on there, and still looking for good performance, and high level of extensibility, you should give it a try. I also added here that V2 is available. We just released it 2 days ago. We are very proud of this release because we improved performance and we stretched JavaScript really to the end of what we can, at least for now. We'll see next year. But yeah, I wanted to say it because it's not going anywhere and it's still here, even though we just launched a new router that is built with Rust. So I want to say that, so we have the Hive gateway, but what was missing and why we built this new router in Rust. So the first thing that our customers asked us for is first a spec and a query planner that you can extend, you can change, you can understand the details. So Federation became the industry standard, and everyone is using it. But under the hood, there is a whole piece of tech that GraphQL developers didn't really see or had the access to understand. So we built a new query planner that is 100% compatible. So that was the first thing that was missing. You can use it with the new Hive router. But as I said before, it's a library. If you want to give it a try and experiment with it in other projects, this is also possible. We're also experimenting with compiling the new Rust query planner as WASM. So this will be shipped in a future release of Hive Gateway. So you'll get the native performance of a query planner in JavaScript as well. So this was the first thing that was missing. The second piece that was missing is, oh, sorry. Before I'll jump to the second one, Kamil will explain the query planner, how we built it, and what's inside. Go for it.
Told you I'm back. Our query planner accepts a supergraph that you're familiar with from Apollo. So if you happen to use like GraphOS, Hive, or any solution, even if you have like built-in registry, and you're familiar with the syntax and the functionality there, it's like compliant with that. That was our base that we used for building the query planner. It's like a knowledge base for the query planner itself. Also the query format. So we wanted to have the knowledge that you have. We wanted to like keep it, so you don't have to learn new things. So that's why we kept the query plan format from Apollo. It's kind of similar. Has like the sequence, parallel fetch, and flatten blocks, plus some others. We wanted to use it until we actually, until it makes sense. For now, it makes sense. We might change it in the future, but it's like future, we don't know. One difference from the Apollo, like the plans, is that we never really put a sequence within a parallel block, which means that we prefers like wider, what I call waves, which means that like those, like we do more tasks in parallel. So it's, I will explain soon. And in practice, what it means is that there's less weighting, and which means the higher P95 and latency in general, which turns into like converts into like more RPS without changing your queries. So the structure, there's like Apollo and Hive because we shared like similar. It's simplified. And by A, B, C, and D is just like an index of the fetch, like the actual HTTP request to the subgraphs. On the right side, you see like the dependency graph of the subgraph calls, and the G depends on D and A, right? So there's like two parents of it. So you can see that like the structure of the Apollo plan is like deeply nested, and it mirrors the structure of the query and its dependencies. What we do is like a very flat plan, organized in like a sequence of waves or like parallel blocks. So what they share in common, so in the execution engine, they both follow the same rules. And one example is when you have like a block which is parallel, for example, in order to get to the next one, you need to resolve all its children. The execution difference is that like Hive aims to maximize parallelism at every step of the query, and this could lead to faster execution times. And this is where I explained the why I think it's the case. So Hive optimizes pretty much for the shortest critical path by doing like a breadth-first approach. Apollo is more like, it's not like 100% true, but it's like more the depth first. And if you assume that like one block is 1 unit of time, constant, so in Hive plans you end up with 4 units for every wave. For Apollo, it's actually 5. And this is the bottleneck. So for example, in this case, when you have 2 parents of 1 fetch step, you see if you go from top to bottom, that within the second parent block in Apollo, you have like 3 blocks one after each other, which create like a sequence. So F waits for, H waits for F, G waits for both H and F. And in our case, we like flatten it a bit. So then when you get to H or G, you already have the H next to it, which is like, if you're like good at math, it's like 5 versus 4. Yeah, and then when I switch to Dotan again.
Okay, so the first thing that was missing is a query planner, and the second piece that was missing for our customers was a faster router, because there are routers out there, but our customers asked for a faster router, even faster than what we could have shipped in JavaScript with Hive Gateway. So this is exactly what we did. We built a new router from scratch in Rust. We invested a lot of time in learning what are the most efficient ways to do memory management, CPU utilization, and all of that. And we ended up with a very fast router. If you want to see the numbers and all the details, you can scan this QR code. Here you can see like an overview of the numbers. If you look at the RPS, then RPS is higher, but also the rest. We have the P95, as Kamil explained, if you do wave planning, and you can minimize the time that you need to do the execution, and then the P95 and P99 are higher. In terms of CPU and memory, you can see we're using less CPU, less memory to do the same work, and even ship more requests. We're very proud of this benchmark. If you scan the QR code, you'll go to the website. We have more scenarios there that are trying to replicate real-life scenarios as much as we can. We are trying to eliminate some factors in the benchmark, so we want to measure only the hot path of the request and to make sure that what we measured is fair and compares all gateways in the same way. So we do an end-to-end test to measure the whole workflow, including network and all other resources. So you can see here, it's very performant, and in terms of reliability, it serves all the requests. These are the numbers. If you want to go deep, as I said, go to the QR code. There is a repository. The whole code, the source code of the benchmark is open source, and we welcome any contribution or ideas for making the benchmark even better or more accurate. So please interact with it. So to the last piece of this talk, we want to explain why it's so fast, because we can claim that it's faster or just say that it's faster, but in practice we want to explain why it's so fast, and we want to push the GraphQL community to learn from the lessons that we had in Rust and in general about GraphQL execution. So Kamil will explain to you why it's so fast. It's yours.
Shows the numbers and I explain the numbers. So we choose Rust. We choose it for like many reasons. One is that we're already familiar with Rust because of the past projects we did for clients and for ours. Second is the benefit of like a native compiled language, which is huge. There's no garbage collection, so there are no pauses for cleaning things up. And you might say it's not a big deal, but then you can be fast with Go if you do this and that tricks, but then you fight the garbage collector. We didn't want to do it, so that's why we stick to Rust. The memory aspect, management aspect of the Rust is also beautiful. The ownership and sharing model is like fantastic. And it's actually helpful when you do like one concept I will explain that later, which is like zero copy JSON processing. So the memory allocation. So what we're doing is called arena management, arena allocation, and arena allocation has like a I mean, first of all, the allocations and their allocations have huge impact on performance. It's every time you do it, it has a cost, and majority of the time we just, what we do is like we use the borrowing and owning patterns, but in some cases we use the arena allocation. It's also known like as a region-based memory management. So think of arena as a group of allocations. So if you have like blocks of memory, instead of allocating each individual ones, you do them by group. So when you no longer need it, as shown here, when the execution of the request is done, you actually remove them all at once instead of one by one. This is like my attempt to visualize the concept, which means every little block, 1, 2, 3, 4, 5, is actually a block of memory. When you want to release it, you do it one by one. It costs you 0 to 9 annotation, and then when you use the arena allocation, it's just done in one go. So there's like a lot of, it's just faster. So another optimization we did is like zero copy JSON processing. What it means that this is the initial query, play animation. So it means that like when router receives JSON data from the subgraph, we actually reuse we like avoid unnecessary serialization and the serialization passes, so we do it as performant as possible. Instead of like deserializing the JSON response into like a JSON tree with own values and copying the bytes over and over again. And by owning, I mean we actually take the byte that we received, we own it, which means like we clone from one block of memory, we put it somewhere else. So instead of doing that, we kind of we reuse the bytes. So this is the visualization. We represent the response. The response that we get is like a block of bytes pretty much. And what we get is like references to those blocks. And then we just deal with the references, which means we just have like a slice of the bytes, and we use just that. So we never really clone or copy. And if we do, it's like very, very, very cheap and efficient. It allows us to actually save the CPU time, reduce the memory a lot, and that contributes to like high throughput. Hive router also reuses the connections per destinations, per origin. So most queries avoid the TCP handshake. And when the gateway is under like a heavy load, we prevent exhaustion of the ephemeral points by capping the amount of open sockets. And when multiple clients ask for the same subgraph calls, what we do is like we do duplicate request by default, which could be disabled if you wish. And of course, we do it only if we can. So for mutations, this makes no sense. So we do it only for queries. And all of that improves the throughputs and protects also the subgraphs during like spikes in traffic. We also run the multi-thread threaded runtime, where each worker, like a thread, has its own queue. So idle workers steal from others, which means that all the workers stay busy all the time. And because the I/O is async and non-blocking, then the thread spends time actually polling the ready state instead of waiting. And the result of that is like higher latency. That translates to like P95 and P99 under like a bursty load. What we also do, so our goal was to be performant from day 0. And to achieve that, we had to eliminate the contentions of the hot paths, on the hot paths. So we don't rely really on the mutexes. What it means is that we don't mutate any shared state between the threads. And requests are mostly handled in isolation, and that's thanks to, because we pass by value, so we give the ownership to the request, or we use just immutable references. And the upstream requests are not affecting each other. One thing is that the threads also don't block each other, and this helps us maintain the high throughput. Yep.
So this covers everything we did in the past year. And we want to talk a bit about what's next. I also want to leave a few minutes for questions, so we'll do it quick. We understand that building a federation router, our GraphQL router, is a lot. There is a lot of features that are needed, a lot of customizations that are needed, and this is our next steps. We are building RFCs now to get community feedback on how they would expect the future router will work. So if you have any feedback or ideas, come visit us at our booth. We are on second floor, and we are the noisy booth there, so come visit us. And let's talk. We have, if you are interested in learning more on the technical aspect that Kamil just explained, we have a blog post that explains it real good with visualization and code examples. So if you want to dive in, go there, and you also have pointers to the source code if you want to look at the details. That's all for us. So thank you for listening, and we have 5 minutes for questions. So go for it. Any questions? Yeah, sure.
We saw how you made it fast, but do you also know what other routers do that make their routers slow compared to yours?
Luckily, they are all open source. So yeah, we know. So the things that we did here are basically the optimizations to make it faster. Because you can, the base implementation that you can take of like doing execution of GraphQL, let's say spinning a few GraphQL requests and then combining it all into one response, like the regular execution flow, is something that all other gateways are doing. But doing the optimization of the memory and avoiding allocations and as much as you can, using references in Rust, this is the magic behind performance. Yeah.
What would you say was the hardest part of building your own router? Was it the query planning, the optimization?
It's yours.
Yeah. So the question was, what was the hardest part of this whole effort? And the hardest part is like literally like query planning, and you face a lot of infinite loops with like 60,000 line of logs to like understand what is the cause of it, and yeah, it's up to you to figure it out, and it's like crazy. But yeah, we kind of did it. So yeah, but it's still ongoing. Like you never know. And learning Rust. For some. I mean, we were familiar, but yeah.
Mm-hmm. Cool. Okay, thank you.
Thank you so much.